Right, the next thing we're going to look at is Newton's law of universal gravitation. So the first thing here that you must recognize is the name of the law. Newton's law of universal gravitation. It is not Newton's law of gravity. It's not the gravitational law. There's no other funny business about it. You must be able to mention that it's Newton's law of universal gravitation. So it's something that you have to memorize. So nearly every person on earth knows what the word gravity means or what the word gravitation means. So when we talk about the difference between the two things, when we talk about gravitation, please make sure you get these definitions into your books. Gravitation is the force of attraction acting between any two bodies of the universe. And that's going to bring us to our next little thing, which is fields, right? Gravity, on the other hand, is the Earth's gravitational pull on the body lying near the surface, lying on or near the surface of the Earth. So that's your two differences. What we're going to be looking at in this little section is we're going to look at gravity. So gravity is associated with the mishaps of, let's say, milk spilled on the breakfast table, to falling off a bicycle, or the fact that we always at all points are glued to the Earth's surface. So gravity is that idea of, let's have a look here, of what goes up must come down, right? It's the reason why things are, objects fall towards the Earth, right? It's reasoning. So the role of physics is to explain this phenomena in terms of underlying principles, in terms which are so universal that they're capable of explaining more than a single phenomena, but many phenomena in a consistent manner. So when we talk about gravity, it's not just about falling. It must be learned with a little bit of sophistication. It must be understood in terms of its cause. So what we're going to look at is the cause of gravity. We're going to look at the implications on structure. And then we're also going to look at how it affects the motion of objects in the universe. Alright, so it's not like, hey, things fall, so therefore I have gravity. There are all these different things that we have to take into consideration when we look at gravity. So, if for example, just get this out of the way. If I have, let's actually just use this. Oops. Okay. Just use this idea here. So two things are happening here. If I have an object and that object moves upwards or away from the center of the Earth, it's going to slow down, right? So if I have a rocket, an aeroplane, anything that moves away from the surface of the Earth, it's going to slow. If I have something that moves downwards or towards the center of the Earth, it's going to automatically speed up. So as you stand on the Earth, if I stand on the Earth, so let's say I'm over here, right? And that's how we are actually. So if I had to look at the Earth, we look like this. That's how we are positioned on the Earth. We're like sticking out, like a kind of a pin cushion. So as you stand on the Earth, you're experiencing a force of gravity. A force of gravity. Right? Now that force of gravity is referred to as Fg, and we've looked at Fg in quite a bit of detail. And when we talk about Fg, you're basically talking about your weight, which means it's equal to mg. Right. Now you basically, if you had to jump up, right? So let's remember I spoke about projectiles. So let's have a look at this idea. You're on the surface of the earth over here, and you decide to jump upwards. So if I had to look at that, that's your body. Your body is jumping in that direction upwards. It's going to reach a certain peak. So from here to here, it's going to slow down. When you reach your peak, you're going to stop for a moment, and then you're going to continuously fall down. But when you fall down, you're going to speed up until you hit the ground there. So when we talk about these kinds of motions, what you're doing is you become, when you jump up, so let's say your motion is jump up, you basically become a projectile. And remember what I said about a projectile. It is affected by just gravity. So you go up, let's say it's a ball, it goes up, it reaches this peak over here. So that's a positive direction. Here it stops, and then it falls all the way to the ground, and doing that, which means it's moving in a negative direction, but it's speeding up. Right. Now, when that happens, the fall that you have is a gravitational acceleration. So you're not just falling like willy-nilly. You are falling with a gravitational acceleration of 9.8 meters per second squared. And we've looked at that in a little bit of detail when we work out our weight. So this happens no matter your mass. All masses do the same thing. When they move upwards, they slow down, they stop, they change directions, they fall down. So basically that is what your motion will look like when you jump. You start, this is very important, this is what I'm doing over and over again. You slow down. Oops. You reach a velocity of 0 meters per second. So let's say you go upwards. At 0 meters per second, you change your direction. And then you fall down, which is a speed up action. And that whole falling down, that motion takes place at 9.8 meters per second. So Isaac Newton compared the acceleration of the moon to this acceleration of all objects on Earth. And he believed that the gravitational forces were responsible for each other, and that it was dependent on, that gravity is dependent on distance. So if I had to look at this situation here, all right, please make sure you get this image into your books. If I have the moon that's out here, right, there's my moon, right, my moon is going away from the earth, so it is slowing down, right? At the exact same motion, even though it's away, it's also being pulled towards the earth. See, there's a pull because it's within Earth's gravitational field. So Earth's gravitational field kind of is this whole zone here, right? I'll maybe put it, right. So what's happening is that the moon is being pulled towards the earth, right? And as it's being pulled, because it's in within the field and it can't come any closer, it starts to orbit and keeps orbiting around here. So for example, if I had Earth here and the moon there, they would have a relationship with each other like that. So this is Earth and this is a moon, right? Now if I was on Earth, let's say that's Earth, and you were here touching Earth's surface, right? Your interaction with Earth is a bit different. It's from here to here. So what was decided by Isaac Newton here is that gravity is dependent on distance. So distance is a factor. But also on top of everything else, he also knew that if an apple was accelerating towards the center of the earth, according to his third law, Newton's third law, the earth was accelerating towards the apple. That means that if I'm looking at these two situations here, they're not the same. Because the difference between the moon and yourself is your mass. The moon's mass is greater than, the mass of the moon is greater than the mass of a human. And acceleration works both ways. So we can apply the third law here, and we can say that the moon is accelerating towards Earth, but Earth accelerates towards the moon. Now how that happens is a force of attraction. Remember, all forces of attraction must come from both parties. So now these two objects, so this moon can be interchanged, the word moon can be interchangeable to human as well. So what's happening is, not only is gravity dependent on distance, but gravity is dependent on the mass of the objects involved. So two things are involved. There must be mass, there must be some sort of distance. So think about an apple minding its own business on a tree. How come it just falls and moves to the ground? Because of gravity. Then he thought about height. So let's just think about it like this. Right? If you think about it like, let's say I have this kind of a setup. Right? This becomes very, very important to us, radius of the earth. We're going to have to look at that. Right. So what he did was he thought about height, and he dropped an apple from the top of a tree, atop of a building, and he came to the conclusion that gravity exists way above the trees. So he looked at, what if we took it further up? So the first thing he looked at was the whole thing from the apple and the tree, and it came down this way. Then he went higher, and he went to a top of a building. He dropped the same apple off the top of the building, and it also fell down. He went to a higher building, and he kept doing the same thing. And then he realized that no matter how far above the ground you were, these things will keep falling to the center of the earth. So he realized that gravity went beyond the tallest buildings. Gravity went beyond the surface of the earth. So the earth then has a very large gravitational field, in such a way that he realized that what about the moon? That the orbit of the moon about the earth could be a consequence of a gravitational force. So, because the acceleration due to gravity could change the velocity of the moon in such a way that if it followed an orbit around the moon. So, how do we get the moon orbiting around the earth? We have the moon that is sitting in Earth's gravitational field. So much so that the velocity of the moon is influenced by that gravitational field and by that gravitational acceleration. So when we look at these things, or we look at these ideas, it's not about if something goes up, it comes down. It's more than that. The earth influences the path of the moon. So if there was no gravitational field, the moon would go right past the earth and go into oblivion. But because it caught onto the gravitational field, then the moon takes this path and starts to orbit its planet that it's within that gravitational field. So you must be able to, in a theoretical way, they can ask you, why does the moon orbit around the earth? So you've got to look at this kind of a diagram. That's why I said it's important that you get the drawing into your book and you interact with the drawing. You could draw this setup and show how the moon's actual pathway is to just move through space in a straight line. But the fact that it came into the orbit, it's actually being pulled down to the center of the earth. But because of the moon's mass, it's not coming to the center of the earth because it is a certain distance away. And the earth keeps it at that distance so that it is able to orbit around the earth rather than crash into the earth because it's so far away. Whereas a person who's on the center of the earth, on the surface of the earth, has a better chance of touching the earth because its mass is so small. That is why humans are attracted to the earth, because our masses are so small, but we're still experiencing a gravitational force, whereas the moon is so big and so far away that it can't come and touch the surface of the earth. It's not in a good enough gravitational field. That is why gravity is dependent on distance and mass. We then get to the law of gravity. So this is Newton's law. Newton's law of universal gravitation. Newton's law of universal gravitation states that every particle with a mass in the universe attracts every other particle with a force, that's important, which is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Now, what we're looking at now is we're looking at planetary bodies. And when we're looking at planetary bodies, we know that the planetary bodies are circular. So basically what we're looking at is that if I had two planetary bodies, my attraction is dependent on, let's say this has a mass and that has a mass. Their masses, there must be a product of their masses, is inversely proportional to the square of their distance between the centers. So I need to know that if I had a circle, going across my circle is the diameter, and from the center of the circle, to the edge here, that is the radius. So R is equal to the diameter divided by 2. That is something or formula that I must just have at the back of my mind at all times, because the calculations are going to be dependent on center of the planets and so on. So this is your definition which you must know of by heart. There's no choice about it. Get it down in your books, get it highlighted. Understand that we're looking at a radius here a radius there, and then that distance over there. So that's something that you have to be able to calculate. Let's look at what the formula is like. So we know that, so here's your formula, that the law of universal gravitation states that every object in the universe attracts every other object in the universe with a force directed along the line of the centers of the two objects, which is directly proportional to the product of their masses. See, there's product of their masses, and inversely proportional to the square of the distance between them. All right, so let's get this formula into your books, please, where Fg here is your force. Let's write here force of gravity. G here is the gravitational constant, which is at 6.674 times 10 to the power of negative 11. Please make sure you don't have to memorize it, because it is a constant. It's on your formula sheet. Is equal to the product of their masses. So M1 and M2 are your masses of your objects, and then inversely proportional to the distance between the centers of the objects squared. Right, so this is important. Let me show you how we're going to do this. You can write the formula as Fg is equal to G M1 times M2 all over R squared. This is how you're going to put it into the calculator. Right, that's the one thing. The other way that you can see this formula, they'll give it to you like this: G M times M over R squared. That's going to be your bigger mass, and that's going to be the smaller mass. Essentially here, it doesn't really matter. But let's say, for example, they give you all the information and they say, give us the mass of the person or mass of the planet. So bigger masses get a capital M and smaller masses get a little m. So I'm just showing you the different ways in which this formula can present itself to you, so that you're aware of how that kind of works out. Right, another thing is your SI units that we use. For Fg over here, it will be in newtons. Your answer will always be in newtons. And if your answer is in newtons, please make sure it comes with a direction, the opposite direction of motion, so on. Your mass 1 and mass 2 must be in kilograms. Always. So if they give you grams, please make sure you do a conversion. Your distance here can sometimes come with the symbol D, and that will give you, it must be in meters with a little m. So if they give you kilometers, you must convert to meters. So for this one, they can give you grams. You must make sure it's in kilograms. That would be considered correct. Incorrect. Here they can give it to you in, and they will give it to you in kilometers. It must be in meters. That will be marked as incorrect. So please notice that here, in terms, we're going to look now at some calculations, but we're also going to look at relationships a little bit later. But what you need to make sure that you understand here is conversions. So a good table for you to make sure you get down in your books is your engineering notations, which look like this: pico, nano, micro, milli, kilo, mega, giga, tera, and so on. Just make sure you know how to do your calculations. Just put it into your calculator and it will kind of sort itself out in terms of conversions and so on. So make sure that you have the correct units. For distance, again I'm saying this, for distance your answers must be in meters with a little m, and for mass it must be in kilograms with the symbol kg. Now let's have a look at some examples. Now let's say, for example, I consider a man and he has a mass of 80 kilograms and he's standing 10 meters away from a woman who has a mass of 65 kilograms, and we want to know the attractive. So let's just have a look at the information we have. But a man of 80 kilograms, he's 10 meters away from a woman. She has a mass of 65 kilograms, and they're asking you for just the attractive gravitational force between them. Alright, so the first thing that you have to do here is you have to get your formula in, right? So you'll write Fg is equal to G m1 times m2 over r squared. Your G here is 6.67 times 10 to the power of negative 11 multiplied by your masses, which is 80 times 65. All of that over 10 meters squared. And that's going to give you a total of 3.47 times 10 to the power of negative 9 newtons in the direction of motion, or you can say attraction. All right, that's your final answer. So the first thing you would have had to do is you had to write down your mass 1, which would have been 80 kilograms. Mass 2, which would have been 65 kilograms. You've got your R at 10 meters. You know G is a constant, so you have that. And then all you're going to do is sub it in. So please make sure that when you're getting into this, you get into good habits. You write down your information because that's very important. And then you substitute it in and you do your calculation. Now let's say, please make sure you're taking down these examples, writing them down, and you're doing the calculation. These are our worked examples so that when we come back, when we're studying and stuff, or we're doing activities, we see how it was done basically, and then we see how it was done more complicatedly. Also, take some initiative, pause the video, do the calculation yourself, see if your answers are the same as mine. Interact with this video. Don't just take down notes willy-nilly. Interact so that you're participating as well. It's not like I'm doing all the work and you're just mindlessly taking down notes. Right, the next thing is, it says now, if the man and the woman move 1 meter apart, then the force is, so same thing now, we've got the same information, except now our details have changed a little bit. So still I've got Fg is equal to G, and I can do it like this, m1, m2, all over r squared, and I'll say 6.67 times 10 to the power of negative 11 multiplied by 80 multiplied by 65, all of that over 1 squared, and that would give me 3.47 times 10 to the power of negative 7 newtons in an attractive force. All right, have a look here at how they're different. Let's have a look here. See there? That what's happened now, as you can see, that the force now is it's a very small force. Now, if I'm looking at these types of questions, you need to make sure you know how to write the formula, your substitutions, your answers with directions. Make sure that you're following all the right steps. And let's look at another one. It says, now consider the gravitational force between the Earth and the Moon. So we've got two things here. We've got the Earth and the Moon. And the mass of the Earth is 5.98 times 10 to the power of 24 kilograms. And the mass of, oops, just reduce this. There we go. The mass of the Moon is 7.35 times 10 to the power of 22. The Earth and the Moon are 3.8 times 10 to the power of 8 meters apart, and they want the gravitational force between the Earth and the Moon. Right, so I've got mass of the Earth. Have a look at my notation, which is 5.98 times 10 to the power of 24 kilograms. I've got mass of the Moon at 7.35 times 10 to the power of 22 kilograms. I've got my distance here at 3.8 times 10 to the power of 8 meters. And then I've got my G value, which I know is 6.67. Alright, so all you've got to do now is the exact same thing. Have a look at how I prefer to write the formula, only because mass of the Moon all over r squared. Alright, so all I'm going to do is say 6.67 times 10 to the power of negative 11 multiplied by 5.98 times 10 to the power of 24. All of that times 7.35 times 10 to the power of 22. And my distance is 3.8 times 10 to the power of 8 squared. So pop that into your calculator, pause the video, and see if you get the correct value. Right, and my final answer is 2.03 times 10 to the power of 20 newtons. The force of attraction. Or you can say in the direction of motion. Right? So, from this example, you can see that the force is very large. So, these two examples demonstrate that the greater the mass, the greater the force. And then we also know that the closer the bodies are, the stronger the gravitational force between them is. So, there's two little notions we can write down. You get this down. The greater the mass, the greater the force. Alright. We can also say, because we have 1 over r squared, that the closer the bodies are, right, the stronger the force. So we feel the gravitational attraction of the Earth most at the surface, since that is the closest we can get to it. But if we're in outer space, we would barely feel it. So two things are important: mass, and then the square of the distance. Right, so distance. Those are the two little things that you have to look at. Now let's have a look at another example. Okay. So just make sure you get that out. Lift up the screen now. When the planet Jupiter, when the planet Jupiter is closest to the Earth, it is a total of 6.28 times 10 to the power 8 kilometers away. Alright, so let's say the distance we have here, is 6.28 times 10 to the power of 8 meters. Kilometers. That's a problem. If Jupiter has a mass, so the mass of Jupiter is 1.9 times 10 to the power of 27 kilograms. What is the magnitude of the gravitational force between Jupiter and Earth? So the other thing we need is mass of the Earth. Now, in terms of mass of the Earth, they gave you mass of the Earth in the previous question. So please make sure you go and double check your notes. That's going to be 5.98 times 10 to the power of 24 kilograms. And we know that G is constant, right? Here's your information that I think that you need to make sure that you know how to process. Number one, mass of Jupiter, they'll give you. Mass of the Earth, you will find on your formula sheet. But if they don't give it on your formula sheet, it will be on a diagram, or they'll assume that you know it. So things like mass of the Earth, mass of the Moon, I would highly recommend that you learn off by heart, because you never know whether you're going to get it or you're not going to get it. Right, so the first problem I have here is that my distance is a little bit of an issue here. My distance is 6.28 times 10 to the power of 8 kilometers. So the first thing I need to do is turn that into meters. What's the best way to go from kilometers to meters? Right, I have to, let's put this here, times by 1000. Right, so I'm going to take 6.28 multiplied by 10 times 10 to the power of 8 and take that whole thing and multiply it by 1000. And I'm going to get 6.28 times 10 to the power of 11 meters. So here's your first question that has you doing conversions. If you don't convert, you're going to get the wrong answer. So you might as well just get it over and done with. Alright, so I'm going to say Fg is equal to G, mass of Jupiter times mass of the Earth, all over r squared. I've got 6.67 times 10 to the power of negative 11 multiplied by 1.9 times 10 to the power of 27. Oops. What am I doing? 27. All of that times 5.98 times 10 to the power of 24. All of that over this mass, which is 6.28 times 10 to the power of 11 squared. And now pop that into my calculator, pause the video, see if you get the same answer. And I've got 1.92 times 10 to the power of 18 newtons in the direction of motion. So you're going to see your answers are very, very big. So what I could recommend that you do is, continuing from our first example, when planet Jupiter is furthest from, Earth, it is 9.28 kilometers away. So the distance is 9.28 times 10 to the power of 8 kilometers away. If Jupiter has a mass of 1.9 times 10 to the power of 27 kilograms, what is the magnitude of the gravitational force between Jupiter and Earth? Mass of Earth, remember I said 5.98 times 10 to the power of 24 kilograms. That kilometer looks a little bit off, so I need to convert that by timesing by 1000. It's going to give me 9.28 times 10 to the power of 11 meters. So all I've got to do is I'm going to say Fg is equal to G, mass of Jupiter times mass of Earth, all over r squared. And I've got 6.67 times 10 to the power of negative 11 multiplied by 1.9 times 10 to the power of 27 multiplied by 5.98 times 10 to the power of 24, and all of that over 9.28 times 10 to the power of 11 squared. And that's going to give me 8.80 times 10 to the power of 17 newtons in the direction of motion. Right. Now let's have a look at those two values. When Jupiter is further then I get 8.8. But when it is closest, I get 1.92. So have a look there how the distance in these two questions kind of functions. So you need to be able to make those sort of, not decisions, but you need to see those kinds of patterns. All right, let's have a look at question 3. Question 3 says, what distance must a satellite with a mass of 80 kilograms be away from Earth to feel a force of 1000 newtons? How far from Jupiter to feel the same force? Right, so in this situation, there are two types of calculations that you need to do. So let's just get down some of our information. The first relationship you're looking at is the relationship between a satellite and Earth. And the second calculation you're looking at is a satellite and Jupiter. Now the main thing that we're looking at here is mass. So we looked at distance, now we're looking at how does mass affect it. So let's write down what information we have. For the first one, for the satellite, we have the mass of the satellite, which is equal to 80 kilograms, and the mass of the Earth, which is equal to 5.98 times 10 to the power 24, and the distance we don't have. So we want to know, we want distance, so we don't have that. And they've given us Fg at 1000 newtons. Alright, so all you do is you write your formula. Fg is equal to G m1 m2 all over r squared. Alright, they've given you your Fg here. Try and do this calculation by yourself. See if you can get to the final answer. So they've given you this as 1000. You've then got 6.67 times 10 to the power of negative 11. Oops. Multiplied by 5.98 times 10 to the power of 24. Multiplied by 80. Oops, what am I doing? Multiplied by 80. And all of that over r squared. Right, the next thing that you need to do is you need to get r squared by itself. So you've got 1000 is equal to 3.19 times 10 to the power of 16 all over r squared. And now what you would do is multiply both sides by r squared over 1. So now I've got 1000 r squared is equal to 3.19 times 10 to the power of 16. And I need to get rid of my 1000. So divide both sides by 1000. Divide by 1000. And r squared is now equal to 3.19 times 10 to the power of 13. And now I just want the distance. So I'm going to square root both sides. And r is then equal to 5.65 times 10 to the power of 6 meters. And I've got that. So that is how far my satellite must be from Earth. The next calculation you're going to do is the satellite and Jupiter. Same thing. Mass of the satellite is 80 kilograms. Mass of Jupiter we know now is 1.9 times 10 to the power of 27 kilograms. We don't know the distance, and we know that Fg is equal to 1000 newtons. Same type of calculation. You're going to go Fg is equal to G, mass 1 times mass 2 over r squared. You've got 1000 here. Again, do this by yourself so that you can get used to working with such big numbers, so that it's easier 1.9 times 10 to the power of 27. It's easier to do the calculations times 80 all over r squared. And then you're going to end up with, again, 1,000 is equal to, so I've done it a different way. You can do it a different way. You only get marks for substituting not all of your working out. R squared over there. And then r squared was equal to 1.01 times 10 to the power of 16. But I just want r by itself, so I square root both sides. And I get r is equal to, 1.00 times 10 to the power of 8 meters. So there is my distance between the satellite and Jupiter, and the distance between Earth and the satellites up there. So it is a bit of a long calculation. Mark allocations work in a very weird way. Let me just show you how that's going to look. One there, one there, one there, probably one there, one there. Here you're going to get for substituting that value in, and you're going to get 1 mark for that. So that is what your mark allocation looks for a question like this. But please make sure you're always substituting. You're writing down the formula. You substitute. You show you're working out all of it as much as you can, and then your final answer at the end of the day. And that's what you get. All right, so there's your 2 answers for this question, and then let's go and have a look at the next thing. Get your calculator into scientific notation. Now the best way to do that is to go on your calculator, go press shift, then go to setup. So shift setup. And then you'll see a whole bunch of numbers going from 1 to 8. You're going to press number 7. So 7. And then after you press 7, it's going to give you an option that does this. You want to press 3. Now 3 gives me 2 decimal places. So I'll press 3. And then I press equals. So now it is in scientific notation. To get out of scientific notation for stuff like maths and stuff, you're going to go shift again, you're going to go setup, you're going to press 8, you're going to press 3, and then you're going to go equals. So this will say SCI, and this will say norm, as in normal. So in scientific, normal. Try and get into make sure you're in scientific notation, only because you are working with such big numbers. It's just ridiculous to be working with all those decimals, because you're going to end up missing a decimal. It's going to mess up your calculations. Right, let's go back to the examples we were busy with. Alright, remember that F is equal to MA. Right, this formula here, F is equal to MA. This tells us that every object on Earth feels the same gravitational acceleration. Right? That means whether I have, for example, let's say I'm on top of a building, and this building is 100 meters above the ground. And from the top here, let's say I drop a book and a ball, right? Exact same height. These two will take the exact same time to reach the ground. Right? In fact, they'll be head to head the entire fall. So on their projection down, they will move at the exact same type of acceleration. Means when they get to the ground here, they will reach at the same time. The reason for this is it's because they are experiencing a gravitational acceleration of 9.8 meters per second squared. So that is F is equal to ma. Now we can show this easily by using Newton's second law and the equation for the gravitational force. The force between the earth, which has a mass of earth, and an object with just a general mass. So what I'll have here is, I know that Fg is equal to F net, right? And we learned that when we did lift problems, right? If Fg is equal to F net, I can equate the two equations. So here we equate. So what I've got here is, I know what G is. This big M here is mass of the earth. And this little m here and that m there is mass of object. Now because I know this is the Fg is equal to F net, I can equate the two, and what ends up happening is we cancel out the m's because they're the same on both sides, and now I've got A is equal to Gm over r squared, which gives me G. Now this G here is the gravitational acceleration of anything that's a projectile that's falling towards the earth. Since it doesn't depend on the mass of the object, because like I just said, whether I have a book or a ball, they both experience the same gravitational force if they are on the same planet and they're falling from the same height. So since it doesn't depend on the mass of the object, the acceleration on the body due to Earth's gravity does not depend on the mass. So we can write that down. We can say that acceleration due to gravity does not depend on the mass of an object. Thus, all objects experience the same gravitational acceleration. The force on different bodies will be different, right? Force is a different thing, but the acceleration has to be the same. Due to the fact that the acceleration, when we talk about acceleration of falling objects depends on gravity. And that gives us a new formula, which is this. If I want the gravitational acceleration on any kind of planet, then the formula I'm going to use is G. I'll just write down what each of these things means. G is the gravitational acceleration. And that answer will always be in meters per second squared. M is the mass of the planetary body, and that's still going to be in kilograms. Move that up a bit. R is still going to be the distance between the object and the planet, and that will still be in meters. And then G is over there, which is still 6.67. So it's a branch of the original formula that we were using, and that is how you calculate the gravitational acceleration. So the fact that the gravitational acceleration is independent of the mass of the object holds for any planet, not just the Earth, but any planet, means that we will have different gravitational accelerations on different planetary bodies. Right? And let's have a look at some examples of how this would work out for us. And I look at my formula. My formula is G is equal to G mr squared. Right. It says the radius of Jupiter is 71.5 times 10 to the power of 3 kilometers. And the radius of the moon, so I've got Jupiter here. Oops. And the radius of the moon is 1.7 times 10 to the power of 3 kilometers. If the moon has a mass of 7.35 times 10 to the power of 22 kilograms, work out the gravitational acceleration on Jupiter and on the moon. Alright, so what we need to do now is multiple calculations, but also let's have a look at our information. And let's have a look at what we've got here. So the first thing I have here is Jupiter. And they're telling me I have a radius here, which is equal to 71.5 times 10 to the power of 3 kilometers. And my mass of Jupiter, I know from previous questions, is 1.9 times 10 to the power of 27 kilometers. All right, great. I also know that I have a moon. This is another one. I have the moon here. And that radius is 1.7 times 10 to the power of 3 kilometers. And it has a mass of the moon is 7.35 times 10 to the power of 22 kilograms. Right. The first thing that I need to recognize here is my kilometers. That's unacceptable. So I've got kilometers here. I need it to be meters. So I've got that sitting now at 71.5 times 10 to the power times 1000. Don't forget that. Times 10 to the power of 6 meters. So that's acceptable. On the other side, I've got 1.7 times 10 to the power of 3. And I need to make that times it by 1000. I'm going to get 1.7 times 10 to the power of 6 meters. So that is the acceptable amount. Alright, so now it says they want the gravitational acceleration on these two planets. Now, all we're doing is, when I'm looking at either one of these, I want to know if I was there. Can you see? If I was on the surface, what type of G am I going to experience? So if I go, so I've got to do the same for both of them. So if I go for Jupiter, I can say G is equal to the mass of Jupiter divided by the radius or the distance, radius squared. So my mass of times G, sorry. I've got 6.67 times 10 to the power of negative 11 multiplied by 1.9 times 10 to the power of 27. And then take all of that over 71.5 times 10 to the power of 6 and all of that squared. And that's going to give me 24.789, which is 24.79 meters per second squared downwards, because that's going towards the center of the earth. And pause the video, try and do the moon, see if you get the correct answer. So we need to work out the gravitational acceleration on the moon. Remember, we converted it to the distance to meters, so I've got G is equal to G mass of the moon over R squared. I've got 6.67 times 10 to the power of negative 11. I can just put all of this into my calculator, multiplied by 7.35 times 10 to the power of 22. All of that over 1.7 times 10 to the power of 6 squared. And I'm going to get 1.696. So I'm going to get 1.70 meters per second squared, also downwards. So what I can see from these two examples is, if I look at, let's take another color, if I look at mass and mass, Jupiter is relatively larger than the moon. So look at that, 24.79 versus 1.70. Now we can use these values to calculate weight. So this is how we understand the difference between mass and weight, that mass is a scalar quantity, weight is a vector quantity, and I can work out my mass and my weight on different planets based on the gravitational acceleration that we have from either one of these. All right, let's have a look at another example. Number 5. Right. Number 5 says, astrology, not astronomy, makes much of the position of the planets at the moment of one's birth. The only known force a planet exerts on the Earth's gravitation. Calculate. A. The gravitational force exerted by a 4.2 kilogram baby by a 100 kilogram father at 0.2 meters away at birth. So nice and simple. I've got F is equal to gm1 m2 all over r squared. I've got my, I don't have the force, I'm looking for that. I've got my mass of my baby, m1, my mass of my father, m2, and I've got my distance. So I've got 6.67 times 10 to the power of negative 11, all multiplied by 4.20 times 100. All of that over 0.2 squared, nice and basic, is 7.00 times 10 to the power of negative 7 newtons in the direction of motion. Don't forget that. Here we go. And that's your first question. Question B, please make sure that you're getting these questions down into your books. It's very, very important. Like I said, these are worked examples. You're going to come back here, and each of these examples have been very uniquely different from each other. In the future, when you're studying, you're going to have to come back and just have a look at how these sort itself out. All right, question B says, calculate the force on the baby due to Jupiter if it's at its closest distance to Earth, some 6.29 times 10 to the power of negative 11 away, right? So let's just have a look at what that's going to look like. All right, the first thing you needed to sort out is your information. You've got your 6.67. We know that the mass of Jupiter here is 1.9 times 10 to the power of 27. We know that the mass of the baby is 4.20 kilograms. And we've got a mass here, and it's in meters, so we don't have any conversions to do. So I've got F is equal to G m1 m2 all over r squared. You've got 6.67 times 10 to the power of negative 11, multiplied by 1.9 times 10 to the power of 27 times 4.2, all over 6.29 times 10 to the power of 11, all squared. And you get 1.35 times 10 to the power of negative 6 newtons in the direction of motion. Right. That's your final answer there. Right, question C says, how does the force of Jupiter on the baby compare to the father on the baby? So if I look here at my two answers, I've got 7 times 10 to the power of negative 7. And here I've got 1.35 times 10 to the power of negative 6. Alright, so first of all, when I look at the two, I've got to do some sort of calculation. So what we're going to do is we're going to look at the force of the father versus the force of Jupiter. Right. Now how we do that is we work with ratios and we do a comparison. So all we're going to do is we're going to say, to get the calculation, I'm going to say force of the father divided by force of Jupiter. And we're going to have, oops, what is that? 7 times 10 to the power of negative 7 divided by 1.35 times 10 to the power of negative 6. And let's see what we get there. And you end up with 14 over 27. And that gives me an answer of 0.518, so 52. So therefore, the force of the father on the baby is 0.52 times the force of Jupiter on the baby. So for a question like this, yes, the question is not asking you for greater than, less than, equals to. It's asking you to compare. And when it asks you to compare, you must do some sort of calculation in order to get through this. All right, so please make sure you get a proper calculation. The calculation we're working with is ratios, and that'll make it a little bit easier. All right, this is a little thing that you need to do. It says find the acceleration due to gravity. So what they're looking for here is for G. On the surface of Mars, use the value 6.42 times 10 to the power of 23 kilograms for the mass of Mars, and the value of 3.390 times 10 to the power of 6 meters for its radius. The answer you should get at the end is that G is equal to 3.73 meters per second squared, and you'll put your direction in. Please take the time, take down the question, do the calculation, see how you fare. Alright, this is another example for you guys to do. Jupiter has a radius at the equator of 71,492 kilometers, and the gravitational acceleration at that point is 23.1 meters per second squared. Calculate Jupiter's mass from its radius and the gravitational acceleration at its equator. So what you're looking for essentially is Jupiter's mass. Alright, the next question is, so that's the first question. Part B, let's have a look here. Part B over here, so here's A. B says, what is the ratio of the calculated mass of Jupiter to NASA's Jupiter fact sheet value of X, Y, and Z? So this value here is your mass of Jupiter that NASA gives us. You're going to work out the mass of Jupiter here, and what they want you to work out is what's the ratio between the two. Now we did the previous examples we've done with the baby and the father in Jupiter. It's very similar to that. Do your calculations and let's see what your answers are. You can, for both questions, if you want to send me a message, I'll give you, for this question especially, if you want to send me a message, I'll give you the solution so you can see if you did a good job or not. Please don't round off unless it's final answers.